Good morning. I am Daniel Crystal Joy C. Agambod, a MAED Math student of University of Mindanao, and I will be explaining or discussing the Cramer's rule or the other applications of determinants as part of the discussion of Group 1 for the determinant. So in this presentation, I will be discussing 10 different subtopics, which are Cramer's rule definition, its formula, the definition of Cramer's rule 2 by 2 matrix, its examples, Cramer's rule 3 by 3 matrix, examples of the 3 by 3, the Cramer's rule chart, the conditions, and lastly, the conclusion. So to introduce the topic, Cramer's rule is invented by mathematician Gabriel Cramer in the year 1750s. This rule is used to find the solution of a system of equations with any number of variables and the same number of equations. So here in the right part of the screen is Gabriel Cramer. Sometimes when we are solving a system of equations in three variables, say x, y, and z, we may need to solve for two variables, x and y, to solve for the variable z. But using Cramer's rule, we can find the value of any variable without finding the values of the other variable. But the Cramer's rule has some limitations with respect to the solutions. This rule can be applied only when the system has unique solutions. But how do we know when a system has unique solution? Let us learn about this along with the definition and formula as well as examples of Cramer's rule along the way. So Cramer's rule is one of the methods used to solve a system of equations. This rule involves determinants. For example, the values of the variables in the system are found with the help of the determinant. So let us consider the system of equations in n variables written in the matrix form Ax is equal to b, wherein A is the coefficient matrix or the square matrix. The X is the column matrix with the variables, and lastly, the B, which is the column matrix with the constant. So let's consider a system of linear equations with n variables. Again, as discussed in the earlier slide. So now we have to find the determinants as seen on the screen. So here, the dx of I, for wherein the I is equal to 1, 2, 3, and so on and so forth, is the same determinant as D, such as the column is replaced with B. Thus, this formula is shown on the screen. And we will be noting that the D or the denominator in the formula should not be equal to 0. So let us further understand the Cramer's rule concept through discussing it specifically in 2 by 2 matrix and later on the 3 by 3. So the Cramer's rule for the 2 by 2 matrix is applied to solve the system of equations in two variables. Let us consider the two linear equations in two variables, which are a sub 1x plus b sub 1y is equal to c sub 1, and the second equation is a sub 2x plus b sub 2y is equal to c sub 2. So first, let us write these two equations in the form Ax is equal to b, wherein, okay, uh, the A is the coefficient matrix here, wherein A sub 1 and A sub 2, as well as B sub 1 and B sub 2 are the parts. The X is the variable matrix X and Y, and the B is the constant matrix, the C sub 1, C sub 2, or the third part of the each equation. So the D here is solved through having the A sub 1, A sub 2, B sub 1, B sub 2, or the coefficient matrix cross multiplied. Okay, and for the D sub X, this will be the C and the B variables. Okay, cross multiplied also here. And the D sub Y is solved from the A and the C variables cross multiplied also. Therefore, we can have the X and Y through dividing the D sub X over D and the B sub y over d. So to understand the concept of the 2 by 2 Cramer's rule and how to solve it, here is example number 1. So solve the following system of equations using Cramer's rule. The equations are 2x minus y is equal to 5 and x plus y is equal to 4. So first things first, given these two equations, let us write this in the form of ax is equal to b as discussed previously. So here, again, the a is the coefficient matrix. So from the given formula, given equations, 2 is the coefficient of x, then -1. Here's the second equation is 1 and 1. So here is our coefficient matrix. And then x is our variable matrix. Lastly, our constant matrix are 5 and 4 from the constant of the equation here in this part. So what we will do first, here we specify the a, the x, and the b. So now we solve for the d. Okay? So the formula again for the d is just the a and the b variables cross multiplied. So again, the a and b are the coefficient matrix. So 2, 1, -1, and 1 as seen on the screen. So we will cross multiply. By cross multiplying, we will multiply the 2 times 1. So here, minus -1 here times 1. So 2 times 1 is just 2, and -1 times 1 times the negative here is will be positive. So plus 1. So 2 plus 1 is 3, which is not equal to 0. Why it is specified that it is not equal to 0? Because we need to know that it has unique solution. So the d should not be equal to 0. Thus, we can proceed. So since the d is not equal to 0, we can solve for the d sub x and d sub y since it has unique solution. That's the rule. So d sub x is equal to our c and the b variables, which as the c, our constant matrix, which is the 5 and 4. Okay. And our b variables are -1 and 1. So we will cross multiply them also, same as the solution for the b. So 5 times 1 here, and minus -1 times 4. So be careful of the sign so that we will have the correct answer. So 5 times 1 is 5, minus -1 times 4 is -4, but since they are negative both, it will be positive. So 5 plus 4 is equal to 9. So that's our d sub x. For our d sub y, this will be our a and the c variable. So 2 and 1, as well as 5 and 4. So we will cross multiply it again. So 2 times 4 minus 5 times 1. 2 times 4 is 8 here. And 5 times 1 is 5. So minus siya because there are no any negative in the second part of the equation. So 8 minus 5 is equal to 3. Thus, we have d sub y, which is 3. Therefore, we can solve for the x and y for the solutions of our two equations. So x is d sub x over d, which are the dx is 9 and the d is 3 with the previous solving method. So 9 divided by 3, that's 3. So that's our x. Our y is d sub y all over 3. So 3 adding d sub y divided by 3, that's 1. So our solution for that question or the equations are 3 and 1 as the x and y. So another example here, still we are in a 2 by 2 Cramer'S rule. So 2 by 2 matrix variances. So the following system of equations using Cramer'S rule. So the equations are 2x plus 5y is equal to 6 and 5x minus 4y is equal to -1. So this is the solution for this. Again, remember that in solving the x and y solutions, the formula are this following. So first we need to solve the d so that we can know that it has unique solutions. So d again are the a and the b variables of our coefficient matrix. So we will just cross multiply them. So what is the a sub 1 and a sub 2? That's 2 and 5 based on the equations provided. So 2 and 5. What are our b variables? That's 5 and -4 based on the equations here. 5 and -4, our y triangle. So we will cross multiply them. 2 times -4 here minus 5 times 5 here. So 2 times -4, that's -8. Negative 5 times 5 is negative 25. So negative 8 minus 25, that's negative 33, which is not equal to 0. So we know that it has unique solutions. So we can proceed with finding the d sub x and the d sub y. So find the t sub x again, we will be needing the c sub 1, c sub 2, b sub 1, and b sub 2 or our constant matrix as well as the y variable in the equations provided. So c variables are 26 and negative 1, and our b variables or the y part is the 5 and negative 4. Again, we will just cross multiply that. So C, 1 and B2, so 26 times negative 4 minus 5 times negative 1. So 26 times negative 4 is just negative 104. And negative 5 times negative 1 is 5. So negative 104 plus 5 is negative 99. So that's our d sub x. So next, our d sub y. We need to have the x variable for the first part of the equation and as well as the constant matrix or constant part, which are c variables. So that's 2 and 5 as well as 26 and negative 1. Again, we will just cross multiply them. So 2 times negative 1 minus 5 times 26 for 26 5. That 2 times negative 1 is negative 2 and negative 5 times 26 is negative 30. So negative 2 minus negative 930 is just 132. So that our b sub. Since we already solved for the d sub x and d sub y, we can now have our x and y solution. So x is just equal to the d sub x over d, which is negative 99 divided by negative 33. So that's just 3. Why there is no negative? Because again, both numerator and denominator has no negative sign. In our y, d sub y all over d is just equal to negative 132 divided by negative 33. So that's 4 without a negative sign since both have a negative sign. So basically, our solution for the problem is just 3 and 4 as our x and y. So we now understand the 2 by 2 matrix of the Cramer's rule. Now we go to our 3 by 3 matrix. So to find the Cramer's rule formula for a 3 by 3 matrix, we need to consider the system of 3 equations with 3 variables. So it is more complicated than the 2 by 2 matrix since they have only 2 equations. So consider these 3 equations, a sub 1x plus b sub 1y plus c sub 1z is equal to d sub 1. So we have 4 variables already. So let us write these equations in the form Ax is equal to b, wherein again, here, our first part is our coefficient matrix or the coefficients of the variables here. Our variable matrix, which are x, y, and z. So we have 3 variables now. And lastly, our d part is our constant matrix or the last part of our equation. So now we need to, again, first solve for the d so that we can know if it is not equal to 0 and we will have unique solution. So our d is the A, B, and C variables part. So take note that since we have 3 equations already, it will be 3 by 3 matrix also in having our d sub x, d sub y, and d sub c. So we take note of this following. So sa d sub x, we will have the d, b, and c variables. For the d sub y, we will need a, b, and c. And as well as for the d sub z, we will need a, b, and d. So therefore, in solving the x, y, and z solutions, we will be needing the d sub x, d sub y, and d sub z so that we can divide it with our d. So to further understand our Cramer's rule 3 by 3 matrix, here is an example solved by me. So solve the following system of equations using Cramer's rule. So given these 3 equations here, 2x plus y minus z is equal to 1, 3x plus 2y plus 2z is equal to 13, and 4x minus 2y plus 3z is equal to 9. So we will be having the equation same as this so that we can know that it's A, B, C, and D na parts. Okay, so take note that we can have our x, y, and z solutions through having this formula. So we will solve for the D first so that we will know if it has unique solutions. So D here is just our coefficient matrix. Okay, so A sub 1, A sub 2, A sub 3, the B part, and the C part. So where do we get the numbers for this so that we can solve? So based from the equations provided, we will get their coefficients since these are the coefficient matrix. Okay, this is the coefficient matrix. So 2, 3, and 4 for the A. Okay, here 1, 2, and negative 2 for the B. And for the Z, negative 1, 2, and 3 here. So we have the coefficient matrix for that so that we can solve for the D. So what we will do next is to have the first uh, row, okay, to be here, and we will cross multiply the parts. Okay, so how do we know the parts? Okay, here I will be having it. Okay, so A sub 1 first, or our 2 here. So we will put the 2. B sub 2 and B sub 3, C sub 2 and C sub 3. Where do we get this? We will just cross out where the column and the row of the A sub 1 is located. So we will have this part. So you can see B and C part are just here, okay? So minus, okay? Always minus here, B sub 1. So where do we get the B sub 1? Okay, so B sub 1 is just here, okay? So we cross it so that we can know that it is from the row 1 and the column 2, okay? So B sub 1 here, then we multiply it to the matrix of the un, um, uncrushed, kumbaga. So A sub 2, A sub 3, and C sub 2, C sub 3, similar to this one. And lastly, we will have the C sub 1. So where do we get the C sub 1 na matrix on the side? The C sub 1 is here, so we will cross it. We're in the third column and first row ang C sub 1. So this is plus always here in a part. That's plus. Here is negative or minus. Okay, so the part here, A sub 2, A sub 3, B sub 2, and B sub 3 are the part of this. So I hope you got it already since we will be solving the following. So here, our B sub 2, B sub 3, C sub 2, and C sub 3 are 2, negative 2, 2, and 3, minus 1, our B1, times 3, 4, 2, and 3 here, plus negative 1, which is our C sub 1, times 3, 4, 2, negative 2. So how do we solve next? Just copy the 2, then we will cross multiply it. How do we cross multiply? 2 times 2, 2 times 3, rather, minus 2 times negative 2. Thus, we have this part. 3 times 3, minus 2 times 4, thus we have this part. 3 times negative 2 minus 2 times 4, thus we have this part. So I hope you got it already. So we will solve. 2 times 3 is 6. Negative 2 times negative 2 is just 4, so positive. Minus 1 times 3 is 9. Negative 2 times 4 is negative 8. Minus 1. 3 times negative 2 here is negative 6. Negative 2 times 4 here is negative 8. So we will have this. All right? So 6 plus 4 is 10. We will simplify. Okay? 9 minus 8 is 1. Negative 6 minus 8 is negative 14. So 2 times 10 here is 20. Negative 1 times 1 is negative 1. And lastly, negative 1 times negative 14 here is positive 14. So again, we simplify. 20 minus 1 plus 14. 20 plus 13 is just 33. So our D now is 33. And we know that it is not equal to 0, so we have unique solution. So we will get the D sub x, D sub y, and D sub z later on. Okay, so we have already the D, which is not equal to 0, so we will proceed with solving the D sub x. So D sub x, based on the discussion earlier, should have the D, the B, and the C. So based from the equations, the D is just the constant matrix, the B is the Y part, and the C is the Z part. So that's 1, 13, and 9, 1, 2, and negative 2, and lastly, negative 1, 2, and 3. So we will be solving that. So D1 is our first row, first column, B1 here, okay, and C1 here. So how do we get again here? Just similar to how we got from the D, from solving the D previously. So again, how do we get it? The D1 is here, so we will crash out where it is located. So we got B sub 2, B sub 3, C sub 2, C sub 3 here. So we got this part. All right, so we will erase that. How do we get the matrix for the B sub 1? So B sub 1 is here, so we will crash out. So our D sub 2 here, D sub 3, okay, C sub 2 and C sub 3 are the following. So how do we get the C sub 1 solutions or the matrix rather? So C sub 1 is here, so we will crash that out, leaving us with D sub 2, D sub 3, B sub 2, and B sub 3. Thus, we got this part. So understood already? So we will have the next part, which is the solving of the cross multiplication. Okay? So we will substitute the numbers based on the parts here. So D sub 1 is just 1, okay? B sub 2, B sub 3, C sub 2, C sub 3 here as just 2, negative 2, 2, and 3. So we will just supply this with the numbers given on the right side of the part, okay? So we will cross multiply. So 1 times that 2 times 3 minus 2 times negative 2, which is this part, okay? 13 times 3 minus 2 times 9, which is this part. And 13 times negative 2 minus 2 times 9, which is this part. So again, be careful of the signs. So we will solve 2 times 3 is 6, minus 2 times negative 2 is just 4 since there are two negative signs. Minus 1, just copy. 13 times 3 is 39. Negative 2 times 9 is negative 18 plus the negative sign. Minus 1 times 13 times negative 2 is negative 26. 2 times 9 is 18, so minus because of the minus sign. 6 plus 4 is 10. 39 minus 18 is 21. Negative 26 minus 18 is negative 44. So we will multiply them. 10 times 1 is 10. 21 times negative 1 is negative 21. Negative 1 times negative 44 is positive 44. So 10 minus 21 plus 44 is just equal to 33, which is our D sub x. Now we go to our D sub y. So there are, they have the same process, okay? Just take note that the parts of the matrix of the D sub y is different from the D sub x. So in our D sub y, we have the A, D, and C na part. So A is our x na coefficients, D is our constant part, and C is our Z na coefficients. Thus, we have 2, 3, 4, 1, 13, and 9, and negative 1, 2, and 3. So same process, we have 66 as our D sub y here. Lastly, for our D sub z, it is just similar to how we solve the D sub x, and the D sub y. Again, take note that they only differ in these parts, okay? On what the coefficients or the constants are. Okay, so for our D sub z, we need A, B, and D parts, which are the x coefficients, the y coefficients, and the constant na part. So we have 2, 3, 4, 1, 2, negative 2, and 1, 13, and 9. So again, we will have this part, okay? So A1 is here. So we have B2, B3, D2, D3 as this part. Okay, so that's in our A1 na part. In our B2 part, B sub 2 part, we have here, so we just cross it. Okay, again. So we have A2, A3, D2, D3. All right. For our C sub 1, so since it is from the column 3, okay, this one, and row 1, we have A2, A3, B2, B3 for our matrix. So next we will be supplying the numbers based from here. So we have this part, all right? So we will cross multiply them. So copy the 2. 2 times 9 minus 13 times negative 2 is in this part. 3 times 9 minus 13 minus 15 times 4 is in this part. All right. 3 times negative 2 minus 2 times 4 is in this part. So we will just cross multiply them. So we now solve. 2 times 9 is 18. Negative 13 minus 2 is 26 positive. 3 times 9 is 27. Negative 13 times 4 is negative 52. 3 times negative 2 is negative 6. Negative 2 times 4 is negative 8. Thus, we have this part already. So we will simplify. 18 plus 26 is 44. 27 minus 52 is negative 25. Negative 6 minus 8 is just negative 14. So we multiply them. 2 times 44 is 88. Negative 1 times negative 25, that's positive 25. And 1 times negative 14, that's negative 14. So we've solved, so we can just solve this. 88 plus 25 minus 14, that's 99. So that's our D sub Z. So now that our D sub X, D sub Y, and D sub Z are all complete, we can now solve for our solution X, Y, and Z. So our dx here, okay, dx is 33. Okay, so I won't write anymore. So 33 divided by 33, that's 1. Okay, d sub y is 66 divided by our 3, our d, which is 33, that's equal to 2. D sub z is 99 and our d is 33 again, so that's 3. So basically, our solution for the problem is just 1, 2, and 3 for our x, y, and z. So after we have solved the different parts, the 2 by 2 matrix and the 3 by 3 matrix, if we observe the formula of the Cramer's rule as we discussed earlier, the definition, the formula, as well as the different examples, we have mentioned that D is not equal to 0 everywhere. Why is that? Because as I've discussed earlier or previously, we need to find the unique solutions. Okay, so this is because while finding the values of the variables, d is in the denominator. So, and if d is equal to 0, the fraction goes undefined. So, dapat hindi equal to 0 sa d so that our solving process will not be undefined. So, but what about the system of equations when d is equal to 0? So, there are two possibilities for this. Number one, the system may have no solution at all, or number two, the system may have infinite number of solutions. So though Cramer's rule doesn't help in finding the infinite number of solutions, so we will not discuss, since the discussion is focused on the Cramer's rule only, we can determine whether the system has no solution or infinite number of solutions using the determinants, which we compute as the process of applying the rule. So if d is not equal to 0, it has unique solution. If d is equal to 0 and at least one of the numerator determinants is a 0, then the system has infinitely many solutions. And lastly, if d is equal to 0 and none of the numerator determinants is 0, the system has no solution at. So basically, the chart or the rule chart of the Cramer's rule here is shown wherein ax is equal to b rather, and if d is not equal to 0, it has unique solution. If d is equal to 0, there are two possibilities: the no solution and the indefinitely many solutions. So from the previously shown chart and explanation, it is very clear that Cramer's rule is not applicable when d is equal to 0. Okay, so we cannot find the solution of the system of equations using Cramer's rule if that's the case. So in this case, we can find the solution using Gauss-Jordan method. So again, Cramer's rule is used to find the solution of a system only when the system has unique solution only if the d is not equal to 0. Again. So for the purpose of reminding, here are some important notes related to the applications of Cramer's rule. So if there are n variables and n equations, we have to compute the n plus 1 determinants. That's number one. Okay, number two note, this rule can give the solution only when d is not equal to 0 if it has unique solutions. Number three, if D is equal to zero, the system has either infinite number of solutions or no solutions at all. And number four note, we cannot find solutions by using this rule when the system has infinite number of solutions. Okay, if D is equal to zero, we cannot use this rule. So to conclude everything that we discussed, Cramer's rule is a method used to solve system of linear equations using determinants, often called the determinant method. However, it has limitations. It only works when there is unique solution if the d is not equal to zero. If the determinant is zero, or if their system has no solution or infinitely many solutions, Cramer's rule cannot be applied. Thus, it is useful method but works only under specific conditions. Okay? So you can read the following frequently asked questions with the answers provided, just like, for example, what is Cramer's rule in the matrix? What it is not, which is determinant method. Does Cramer's rule always work? Which we discussed already that it is not working always because of the specific condition. What is the limitation of Cramer's rule? So we go back to the chart, okay, our rule chart. And in what condition does Cramer's rule fail? Okay, so we already discussed, and I hope you understand our lesson or our discussion on Cramer's rule, the definition, the formula, the 2 by 2 matrix, their examples, the 3 by 3 matrix, their examples, the rule chart, and the limitations and everything. Thank you so much for listening to our discussion on the Cramer's rule or other applications of determinants.